Okay, I think I'm going to get started. While people are still joining in, I will admit them accordingly through the chat window. So we have co-organizers over here as well. So please admit people as they join. Okay. So thank you for that. And yep, welcome everyone to today's Lunch and Learn session. My name is Yushi Tan, and I will be the presenter today. We will be talking about running CST simulations using HPC or high performance computing. So please save all the questions until after the presentation. So by default, the meeting has all the attendees muted so that we do not disrupt the flow of the presentation. So we're going to answer the questions in the Q&A section. So please type in your questions in the chat window. Okay. So without further ado, let me get started. So I want to talk about the motivation of this Lunch and Learn session. So why do we use high performance computing or HPC? So over the past 20 years, computer hardwares have become way more accessible than ever before. So we have basically a pretty capable computer in our hands every day, right, in the phone. So these hardwares are way more powerful compared to previous generations, either providing a higher clock speed or you can get more work done at the same clock frequency by using a better architecture, right? So it makes sense to write computer codes to take full advantage of these improved hardware. So what is the end result that we would be expecting? So we expect some kind of dramatic speed up, right? To who doesn't like to see a simulation running a lot quicker? So some of you might have heard of GPUs or graphics processing units. They offer much better performance compared to using CPUs with certain methods because of the higher bandwidth. So it makes a huge difference between getting a solution in a day compared to 1 week, right? So that's the motivation why we want to use HPC. So due to the limited time we have, I'm going to focus on 3 main acceleration techniques here. So the first one is CPU multi-threading. I'm going to explain what it means in a little bit. The second one is GPU computing. And the third one is distributed computing. Okay, I'm going to focus on three topics. So all it boils down to is efficiency. Okay, so we want the simulation to be able to give us a solution in a shorter time, right? So a CST's approach has always been to provide complete technology, at least with modern licensing, right? So by modern, I mean 2018 and after. It means that you have access to all the application-specific solvers, okay, on the 3D side. So it's beneficial to use the most appropriate solver to solve the problem because you have access to all the solvers anyways. So for example, let's say you are dealing with a wideband antenna problem. So it would be more efficient to use a time domain solver. Okay. On the other hand, if you're dealing with a electrically very small antenna with narrow band, then you would use the frequency domain solver. And of course, with you able to access all these solver technologies, you can mix and match. Okay, so basically dividing and conquer. So let's say you have some kind of system that you are dealing with. In this case, a horn antenna just facing the reflected dish. You can use the time domain solver to solve just the horn antenna, and then extract the near field distribution from in the surrounding space near the antenna, and then using this extracted field source as an excitation in the integral equation solver, basically giving you the best of both. Okay, so the end result will be very comparable. Okay, so you can use the hybrid solver technique to tackle a problem. So all this we talked about is on the software side, right? So we using the most numerical, efficient method to solve our problem. Now, what about hardware? If we have better hardware, can we use that? Of course, right? So we can use better hardware. So let's say you have some kind of bottleneck. You have using CPU. It's not as fast as you would like. So the natural response would be to use a better unit, a faster unit, or bigger unit, right? So that's approach number one. And approach number two would be to use multiple of these units, so we can run things in parallel instead of series. Okay, so that's the other approach. So that leads me to the CPU multi-threading. So modern CPUs have multiple cores inside. So I want to talk about CPU multi-threading. So by multi-threading, we really mean multiple physical cores inside the CPU. Okay, I'm going to talk about the licensing a little bit, and you already have access to some of that. already. So let's talk about the most frequently used solvers in frequency domain and also time domain. I'm going to talk about the frequency domain first. Okay, so as we look at the number of cores available, so in this case, 1, 2, 4, 8, 16, 32, the frequency domain or the finite element method solver is mainly compute bound, meaning if we have more cores to throw at it, the solution gets done a little quicker. Okay, so we can kind of see that it's almost a linear ramp up when we increase the number of cores compared to the solver speed up. The solver speed up means, you know, compared to, let's say, 1 core, 1 is the baseline, right? So let's say you have 8 cores, you would, you know, expect a speed up of 6 compared to using 1 core. And you have 32 cores, you would expect a performance increase in around 13 or so. So as it's a linear relationship, somewhat of a linear relationship, by increasing the number of CPU cores, you decrease the simulation time. Okay. Now, on the other hand, and I know some of you use the time domain solver quite a bit in the finite integration technique, FIT, and also the TLM solver, transmission line matrix method. Okay, so the similar logic applies here, but the time domain is mainly memory bound, meaning that the memory modules trying to compete access to the memory control through the memory controller to communicate with the CPU. So the main thing over here is memory bandwidth. Okay, so I'm going to talk about GPU computing in a little bit. It's directly tied to this memory bandwidth. Now, looking at this chart over here on the left, we see a similar relationship. It's probably not as dramatic, right? So if we see the using 1 core as a baseline, now if we increase it to 32, we are looking at less than 12 instead of 13 or 14. So the performance is not as high, but nonetheless, if you have more cores to throw at it, the performance generally increase. And most modern CPUs will have, you know, cores in the 16 to 32 range if you're using some decent system. Okay, so the two methods, frequency domain and also time domain, can benefit from multiple CPU cores. Like I said, I'm going to talk about the GPU computing in a little bit. Now, let's talk about some licensing that most of you would be interested. All of you have access to this. Okay, so on the bottom, you can kind of see that maximum token consumption means 0, right? You do not need any acceleration tokens to take advantage of the configuration shown over here on the top left. Meaning, you can take advantage of up to 2 CPU devices. By 2 CPU devices, we mean 2 CPU sockets on the same motherboard, okay, with the same license. So now 64 threads means 64 physical CPU cores, okay? So that's per CPU. If you can find a CPU with a high core count, by all means use it, okay? It does not require any acceleration tokens to take advantage of that, okay? So now the next 2 that I'm going to talk about does require some kind of token consumption. So the next topic I want to discuss is GPU computing, meaning we are using GPUs to speed up our calculation. So to take advantage of this, you do need the GPU acceleration token. Okay, so let's take a look at some common NVIDIA GPU devices. So on the left, we have the P100 and the GP100 in the Pascal series. And in the middle, we have the V100 and the GB100 in the Volta series. And if we compare the 2 series, the main thing that stands out would be the memory bandwidth. And of course, the different cards would offer different memory capacity. And also the single precision and the double precision, you can kind of see the performance difference over here. So the Volta series offers better performance, right? Because the newer generation card having higher memory bandwidth, and then the single and also double precision are also better. Now, for these cards tend to be pretty pricey, okay? Now, if you have access to, let's say, the RTX 6000 or 8000, personally, I'm using an RTX 3080 card. It offers pretty decent performance already. So now I want to highlight the single precision and also the double precision. So when do you need the double precision? It's when you run select solvers, mainly in the PIC solver, the asymptotic solver, and the integral equation solver. So these 3 solvers require good double precision performance. So the Volta and also the Pascal series cards will offer that performance. Now, if you're running the time domain, the RTX card will work just fine. Okay, so in my experience, the speed up is around 5, which is pretty good. Okay, so next I'm going to show you different models and their performance. But before we get there, let's talk about the typical performance and gain a better understanding of what's behind the scene over here when we do use the GPU. So what kind of speed up we would be expecting. So if we're looking at this from the left, so as we use GPUs, now we would expect some kind of performance increase. Okay, up to a certain limit, right? So the second line, the second orange line in the middle, the dash line in the middle over here means that the GPU memory has been reached. So let's say you have 32 gigs of GPU RAM on board. Once that's reached, you would basically swapping information between the CPU and the GPU. Now that decreases the performance. All right, so that's the situation we try to avoid. We wanted to keep it at the peak performance, right? Using these GPUs. So that has direct relationship with the GPU memory. So as a very rough rule of thumb, we would expect each gigabyte of GPU RAM to be able to solve around 8 million mesh cells. Okay, so just as a rough rule of thumb, use that as a guide. Now, we don't want to exceed the number of GPU RAM. So let's say 32 gigs of RAM allows you to solve around, 32 times 8, okay, times the number of mesh cells that you would be expecting to solve in the millions, right? So we try to avoid the model size being too large. When it becomes too large, it basically defaults to the CPU performance, which is not what we want to do because you're not taking advantage of the GPU. So what happens at that point? You basically just add another GPU to be able to allow you to solve a bigger model. So that's basically what it means. So now I do want to talk about some factors that affect the GPU memory consumption. So dispersive materials, lossy metals, and also open boundaries, they do contribute to the GPU RAM consumption. So but most practical models, if you do have to use some kind of dispersive model, you have to use it, right? So just keep in mind that these factors will affect the GPU RAM consumption. So next, I want to talk about the scalability when it comes to the time domain. So what happens when you have multiple GPUs at your disposal and you just happen to have tokens, right? So using the CPU as a benchmark, let's look at the one V100 card, okay, using the Volta series. So the speed up is around 2.5 or so. Now, if we double the number of V100 cards, we see a speed up factor about 4.5. Okay, now if we double that, right, now into 4 cards, we can see that the speed up factor is around 9. Okay, so if you do have the hardware, you should take advantage of it, provided that you have enough acceleration tokens, right? Now, if we double that again to 8, we can see that the speed up factor is not really 18, right? Because it's there are some tapering effect going on. So the sweet spot is around 4. And most of you would probably, ask the question, how many acceleration tokens I'm going to need to take advantage of up to 4 GPUs? So the answer is 3. You only need 3 acceleration tokens to take advantage of up to 4 GPUs. Okay, so it's not really 4 tokens for 4 GPUs, 3 tokens for 4 GPUs. So the next slide, I want to show you the typical comparison on various models when it comes to using different cards compared to using CPUs. So on the very left, we have the K80 GPU, which is pretty dated in today's standard. Now, the second one is the P100, and the third one is the GP100, also in the Pascal series, and also the Volta series. So you can kind of see that, the Volta series provides you the best performance out of, all these group of GPUs. So the speed up factor in this case, even if you have access to an older card, it's still pretty decent, right? Let's say 3 times the performance compared to using CPUs. You get the solution in 1/3 of the time. Now, if we look at some of the extreme cases, let's say a PCB board, right? Now, using the Volta 100 V100 card, you get a speed up factor of 10 compared to using CPUs. So that's a huge difference. You get a solution in 1 day instead of 2 weeks. Okay, so that's a big difference. I mean, of course, that's somewhat the best model, you may not be running PCB boards, right? So that's why various models are shown over here to kind of give you a sense of performance when it comes to your typical application. So when it comes to GPU consumption, the number of tokens required, if you have one GPU, the number of GPUs means the hardware acceleration devices. You need to check the hardware acceleration checkbox in order to tell the solver to use GPUs. Okay, now by default, like I said, with no acceleration tokens, you can take advantage of up to 2 CPU sockets and up to 6, however many cores that is on board. Okay, by default, CST would take care of, should say, take advantage of all the CPU cores available, all the physical CPU cores available. Now, if you wonder how many tokens I'm going to need for, let's say, a situation where I have multiple CPU devices or multiple GPUs. So this should be a pretty good slide for you to determine what is needed for each configuration. And of course, you can go back to the dialog. In the previous dialog, the GPU acceleration, the acceleration dialog, to play with the numbers to get a sense of how many tokens it's going to be needed for that specific configuration. Okay. Now, the last but not least, I like to talk about the distributed computing. So basically a way to manage your different jobs. So let's say a scenario where I have 2 front ends and we have a DC main controller connecting the front ends to the DC solver servers. Okay. Now, so front end number 1, I have 3 jobs to submit to the DC solver servers, right? And user number 2 has 4 jobs to submit. So now the job is going to be sitting at the DC main controller when all the DC solver servers are occupied. When the solver frees up, then the DC main controller will push the specific job to the open DC solver servers. Okay, when everything's done, the result's going to be transferred through the main controller back to the front end, so you can kind of look at the solution. So let's talk about what tasks can be distributed. The first one, if you're using a time domain, it will be excitations or the number of ports. So typically when it comes to antenna arrays, you would have multiple of these ports or excitations available. So you can distribute these ports. Now, the second one is when you run a parameter sweep or optimization. So all the solvers support DC, so you can distribute these parameter combinations. Then the third one is when you use the frequency domain or the integral equation solvers, you can distribute the frequency points. And if you have enough of these frequency points, you get your solution. So basically just divide and conquer in some way, right? So using distributed computing. Now let's take a look at the scenario for distributed computing to see how many you're going to need. So 2 acceleration devices. To enable the distributed computing, you need to check the parameter sweep optimization up to a certain number of parameters that you're trying to distribute. Like I said, play with the dialog box so you know how many acceleration tokens is going to be required. Okay, so now if you have the number of servers, let's say you have 2 servers or 4 server system, now the speed up is not directly linear, but it will be close to that. So as you can see, 2 servers gives you a performance of almost 2. Okay, now 4 servers give you a performance of 3.5, 3.6 or so, not exactly 4, but it's very close. And of course, in this case, to distribute 4 parameters using the 2 CPU socket motherboard, we need 2 acceleration tokens. Okay. And what if I only have access to single CPU socket servers, right? So I would change the number to 1. And if I'm only distributing up to 2 parameter sweeps, then I need 0 acceleration token. So like I said, play with the dialog to get a sense of what's needed to take advantage of up to the certain configuration that you have access to. Okay, so that's all I have, and we can answer any questions that you have. And again, the questions can be typed in the chat window if you have any. Okay, I see some questions or comments being typed. Yes, Aaron, I can send over the slides in PDF format. Yes. I will follow up with you. Yes. Yep, Ibrahim. Yes, I will send that to you as well. Yep. So let me just send the slides in PDF format to all attendees. And the meeting is being recorded. So after the presentation, you would receive. I'm going to send the recording link as well, so that everyone has some kind of reference to this. So Alexander is asking, can CST decide independently whether the selected settings is sufficient for the model? To answer that question, you should receive some kind of dial messages in the messages window as to whether the hardware setting is suitable for your simulation. Let's say, for example, if you have a 100 let's say 5 million, 500 million, I should say, model. When you're trying to jam that into let's say a 24 gig a GPU, it's gonna give you some warning. Okay, and oh yeah, yep. So in this case, there's a follow-up question. So how should I know if my tokens are sufficient or not? So back to our slide over here. See over here. So tokens available, currently available. So you have the number inside the bracket means how many you have available. So the number up here, the max token consumption, is what's required for the current configuration. So if this max token consumption number exceeds the tokens available, then that means you do not have enough token to run the simulation. Does that answer the question? Yeah, pay attention to this bottom frame token usage. If it exceeds, then you are not able to run the specific simulation. Then you have to decrease the parameter sweep, a number of parameters, or the number of CPU devices, or the number of acceleration hardware acceleration devices, etc. Okay, so yep, Alexander is still typing. I think there's another question coming in. So Ray is asking, what determines the number of threads in CPU acceleration? Okay, so Ray, the answer to that is CST will always try to take advantage of all the physical cores in your CPU. So you can set it to a high number. Let's say the number of multi-thread, right? You can set it to, let's say 50. Okay, if your CPU only has 32, it will use 32. Okay. So I hope that answers your question. So Alexander, there's a follow-up question. Rather, the question that I know whether my discretization of the model is possible too high for my available tokens. Okay, so I think if I understand the question correctly, you are trying to use GPUs to run your simulation, and you want to know whether the okay, good. Whether the model that you're running is too big for the GPU. Like I said, back to the rule of thumb, for each gigabyte of GPU RAM, you are expecting to solve around 8 million mesh cells. So if that number exceeds, so let's say you have 10 gigabytes of RAM. Okay, now if you have 100 million mesh cells, okay, you are getting very close. So now the boundary, the dispersive material, etc. The all these factors will kind of give you a sense of whether it's enough or not. And during the simulation in your messages window, it's gonna show you some warning messages or error messages. Okay, if you see error messages in red, that means you are not able to run the specific simulation. You're gonna get some information during the solver run to tell you whether it's exceeded or not. Okay, so Frank Alexander's still typing. Let's see. There's a follow-up question. I mean, I'd like to come back to the slide over here. Between the swapping, you still, let's say assuming over here, right? So now maximum capacity is right here. Now, it's not to say that, if we exceed it to, let's say 110%, right? It's still offering some kind of good performance. Now, even with the swapping going on between the GPU and the CPU, you still have some speed up factor shown over here. Now, this line over here, so typically at the 150% mark, like you're exceeding the CPU or the GPU RAM limit. So that will basically just, defaults back to the CPU performance. Of course, you're talking about reduced performance, right? So this is at 150%. I mean, it's gonna give you a sense of what it is, but you never want to come over here, get close to it anyways. So that hence the general guideline of using each gigabyte of GPU RAM allows you to solve around 8 million mesh cells. Okay, so that way you can still get the best performance out of your GPUs. So, but can I see? Okay, so if we are running this in a batch mode on an AWS server, I can only see these messages later in the log. Yes, if you're running batch mode, that is very true. So using the 8 million rule of thumb, that should give you the very conservative estimation as to how big of a model your GPU can handle. And of course, you need to know beforehand how much RAM is on the GPU itself. Yeah. Okay. Any other questions? Okay, no problem, no problem. I hope it was helpful. Okay, all right. So I think we do not have any pause typing. Okay, good. Yeah, you're welcome. You're welcome. Hope you guys find it helpful. And I will send the recording link and also the PDF slides to all attendees over here. Okay. Thank you very much for joining. And I know there's you're taking time out of your busy day to attend this. Appreciate it. Okay. Yeah, I will follow up with you guys. Okay. Have a great afternoon, everyone.